Hello, this is lectures on mechanics of materials, and today lecture topic is on transformation of strain. We also will be using equations for transformations and the Mohr circle. Here our motivation is how we measure strain. So that this transformation of strain, the rules that we will learn today, will help us to do experiments and measure strain at the point of interest. In particular, and we will talk about this in more details, is that when we measure strain at a point by a strain gauge, so we measure that typically only in one direction, but then we all remember that strain is a tensor, or you can be written as a matrix, and it has different components. So normal strain is similar to stress, and a shearing strain. So, and the question would be then how we would measure shearing strain while we have only the strain gauges that measure strain in normal direction. All right, but first let's go into our equations and derive what is needed for this type of measurement. First of all, we will be simplifying things and we'll be talking about 2D situation, which is here is a plane strain. So plane strain would mean that we don't have a deformation developing in the third direction. So we are constrained in 2D. So this is quite possible. So for example, we can easily constrain our body or some structural element by some fixed support, some rigid plates, for example, and then we don't allow any deformation, any changes in that out of plane Z direction. So we still can obtain deformations in plane because we're loading material will deform, and so there will be something happening, but only in plane. So we constrain the direction in Z direction. Okay, so then what will happen is that we eliminated all the components that have the index Z in it, right? So there is no normal strain in this direction, we constrain that, but there are also no shearing in this direction, right, in direction Z. So this is our plane strain conditions. So still, yes, we do have deformation, obviously in plane, so all these that contain only X or Y, they in general can be non-zero depending on how we loaded that in plane here. So the difference with plane stress, this is important, is that in plane stress we could obtain only didn't have stresses in that direction. Here in this situation, obviously we can have stress, most likely we'll have stress in that direction, because you can think about these rigid plates that you need to push on them to actually to prevent the material deforming into this direction as we deform it in plane. Okay, let's summarize that. So in plane strain we don't have deformation, we don't have strain in the out of plane direction. But the stress actually can be non-zero. In most cases, it will be non-zero, right? And plane stress, again, we don't have stresses in this direction, right? So this is important, but we can have deformation in the direction. So this is the difference between our plane strain and plane stress. And today we are specifically talking about plane strain, just to simplify our equation so we don't have too many terms and components in our transformation equation. So this is 2D plane strain condition. So this is our state of stress and state of strain. So there's a point Q, and as usual we identify an element around that, a small one. And then we start looking after what happens with this element around that point, how that is distorted, right? What is the deformation that we cause at this point? So we looked into that before, and we defined our strains in the normal direction in y and in x, so that will be our normal strain, so that's the change in the length of these corresponding elements. And we also have shearing strain gamma with the indexes x and y that defines the change in the angle, right, of that element. So as we distort the element around point Q. So this is our coordinates y and x. Undeformed state, then we applied loading, and then we deformed it into the deformed state. Now what we do, we define a new coordinate system by rotation from the original one. So there is some angle theta that defines our new coordinate system. Well, obviously that point of the material will feel exactly the same as here, so that's exactly the same identical state. But now in this new coordinate system, of course, the components of strain will change. It will describe exactly identically the same state of strain, stress, but the components will be different. So again, we have here y prime, x prime, y prime. So that means that we are talking about the measurements in the new coordinate system x prime, y prime. Okay, so that's what we are after, and so we will not follow the derivation of this, how we transform the epsilon x and epsilon y and gamma xy into epsilon x prime and epsilon y prime and gamma x prime y prime, but there is a certain process that we can follow by using the trigonometry, and so you can read more in our textbook here. But at the end, if we do all of that, what we obtain is the following system of equations that transforms our given state of strain in epsilon x, epsilon y, gamma xy into the rotated one system here, right? So this is the normal strain in our new coordinate system, epsilon x prime, here is epsilon y prime, and here is the shearing component x prime, y prime. If we look now into the structure of this, what we immediately will realize is that the system is very similar to what we already had for stresses. And this makes sense because basically stresses are related to strain by linear law. So there is a really linear relationship between stress and epsilon, and so that's why these equations are similar. They're similar, but they're not identical. So you can see that there is that factor 2 appear with the here, for example, with the shearing strain gamma xy, and this is because how we define this gamma shearing strain through the change in the angle. So we have this factor half here, and now we can compare it to what we had before. So the structure is for stresses, for stress transformation, and so you can see that the structure is exactly the same with the only one exception when we have shearing component. So here we don't have this factor half, and here we divide by the factor 2. So this is the difference between this. So, but they are very similar, and there is a reason for that in the relationship between stress and strain. Okay, so now we can, if that's the case, right? So if there is such a similarity, so we can use the Mohr circle too for that. So there is no problem with this. Okay, let's look into that, how that will look like. All right, so here on the y-axis, we still have shearing, but remember this factor half, right? So that's where we put it here. So we don't have tau as we had in when we had Mohr circle for stresses, but we have half gamma. So that's because of that factor. So it's just important to remember to measure this coordinate in half gamma and not in the gamma. And here on the x-axis, so this is symbol, we have epsilon. And that will be our Mohr circle with the radius, with the coordinate of the center, which we can easily define. And so we will also talk about the sign convention, but again, just to mention it, that if it's the shearing tries to produce rotation clockwise, it's positive, counterclockwise is negative. That was also the case for Mohr circle for stresses. Okay, so this is for so that's for our initial state, right? The coordinates of the initial coordinate system x and y, so no primes here. And now we can use this Mohr circle to actually transform and see how the stresses change as we go to a rotated system, right? Or we can find our usual important situations when we have a maximum value or minimum value of the deformations that we apply, right? So there is an angle that makes us rotate to the state which is called the principal state. And when we have principal stresses and principal strains, so when we find the maximum values in that rotation for the original state, we obtain a situation when we don't have any shearing. Remember that we didn't have any shearing stresses in this case, and we also obviously don't have any shearing strains in this case. So this will be minimum, this will be maximum values of strain here. And in this similar, we can also find the maximum value, but we remember what we were talking about a lot, that we are considering here only 2D case, so we need to say this is a maximum value of shearing strain, but only in plane. So then the equations for the central point C and for the radius can be written very similar way as we seen them for stresses. And here is just again to remember that we don't have the shearing component gamma only, but we need to divide it by 2. So that's how we redefine things in our equations of transformation to make them look like an equation for a circle. Okay, and then very similarly, we have the angle which can be defined through the measure of the shearing strain and normal strains. So we can find that principal state here too. And just to remind that we have a sign convention here. Again, we are positive. We have positive shearing to put in the Mohr circle coordinate system if it causes rotation clockwise, and if it causes rotation or tries to rotate the element counterclockwise, so then we will have a negative value of rotation. So next we will look into an example of the strain state which is defined here. So we are given a certain state of strain. So in x direction there is no deformation. In a y direction we have tensile deformation of a certain level, 320 microstrain. So we have negative shearing xy, and that's basically all of it. All right, so then we are given the angle for rotating of our element, so to a different coordinate system x prime, y prime. Okay, so we're given that angle, and so we will look how that will transform our equations here. And of course, so we want to calculate how this state of strain will be redefined, how these components will be written in this new coordinate system with a given angle. So what we are asked to do is to do it first through the equations of transformations, and then by looking into the Mohr circle. Okay, let's start from the simple one, from the equation of transformation. So then we basically will just use this system of equation to write our values, to calculate the values for epsilon x prime, epsilon y prime, and gamma x prime y prime. So components of strain in our new coordinate system. Let's start from the normal component x prime, so that the one that will act here. So remember, so first we started that that normal component in x is 0, but maybe we will not obtain exactly that here. So here's our equations. Again, all the input is here, epsilon x, epsilon y, difference between them, and the shearing component, gamma xy, and we have the factor of 2 here. We still remember that, and here's our angle of rotation, actually the double of that value, right? 2 theta. So that will be 60 degrees here and 60 degrees here. So now we can just substitute. So epsilon x is 0, epsilon y is given as a positive, so it will appear here, here, and here we still have the minus. We'll divide it by 2, so we will have 160 here and here. Okay, and our gamma here will be minus 50 microstrain because we divided by 2. Thus, all these numbers together, we obtain a positive, not a very significant, but positive normal strain in x prime direction. So now, next let's deal with epsilon y prime. Similar formula for that. The only thing that you will see is that the difference is this minus that appears here. Otherwise, it would be very similar to what we just calculated. So we can just use the same values here, but not to forget to put minus here, so that our value for normal strain in y prime direction here. Okay, so again, this is minus, which makes this positive, plus 160 microstrain, and then at the end we have the value of 283 microstrain for epsilon y here. So a little bit lower from what we had here, but still didn't really change very significantly. Well, finally, from the transformation equations, we will just find the shearing component in the new coordinate system x prime y prime. Basically, just substituting here the numbers, epsilon x originally still 0, and for this we are given the numbers and can substitute them. Very good. So here is the our values. So we just substitute them, and the calculation at the end produces a significant shearing, right? So that was basically doubled. So the part of the normal strain that we applied here was now transformed into the shearing and into the little bit of normal strain in x prime direction. So that's how all that played together. All right, so basically we already answered our questions in question point A. So we just used the equations and we obtained all the numbers based on that. So now we want to confirm, or at least look how that will look if we use Mohr circle and get some intuition from that. Let's go with it. Okay, so we will need our coordinate system, in which we don't forget to have this factor of half with gamma. That's how we redefined our circle equation, the Mohr circle equations, through half gamma as a coordinate here. It was more convenient for us to do. Now we remember that. Okay, so first sign agreement. So in fact, for us now, as we write a state of strain, so we have a negative value of shearing strain, right? Well, first of all, we have 0. We already talked about x direction, so for strain, which is 0, that's why you don't see any arrow here. And positive tensile loading for strain with magnitude 320 microstrain. Okay, now with shearing, we have negative minus 100. And as a state of strain, they all will be negative. So that's how they defined. Now we have a different agreement for the signs, for the coordinates that we use in a Mohr circle. So some of them will become negative or positive because of our agreement if that rotates clockwise or counterclockwise. I already can see that this pair, right, so that it needs to be in a different direction of rotation to keep this element in equilibrium. Right? We cannot put them in the same direction, otherwise they will start rotating this element. So they are the same sign minus, but for us, when we put the coordinates here, one of them will become minus and the other will become plus. So we need to identify all these that rotate clockwise, so they will be positive. So basically this one and this one. And these who try to rotate the element counterclockwise, this one and this one, they will be negative. Okay, now we are looking at phase x, and that will be our first point to coordinate to find the coordinate that we put here on our Mohr circle. And on the phase x, what we find is that our strain, normal strain, is 0, and we have only shearing strain that actually appears to be positive, right? Because it tries to rotate the element clockwise. And we remember that we have this factor half here. So we don't take 100, we take 50, half of it, 50 microstrain. Now let's go to phase y, to the second point for us. So here we have two elements. So we still have rotation here, but now that will be in the counterclockwise direction, and so that's why it is negative. And of course the tension here is applied, and so we have a positive strain. So basically here we can plot our circle, right? So we can also identify the central point for that, which will be exactly the half of the this value of the average of the strains, right? So that will be 160. And here we can put our points on the Mohr circle. So here is these two only lines that connect them. It goes through the central of the point, and then we have the radius here that calculated from here. But basically, that's our Mohr circle. Okay, so radius is also can be calculated based on the formula that we were provided, so that what we will have is, so we still have 0 strain for x. This is 320, and so here is our shearing stress that is given here. Substitute that, divided by 2, and then we obtain 167.6 microstrain is the radius of that circle. A little bit more than the central point, right? Coordinate, and that's why we have this circle here going into the negative part, with the coordinate here would be minus 7.6 microstrain, right? So right here. All right, so then we can now go to calculations of our new state, right? So we're going to rotate for our system counterclockwise for 30 degrees. So we have theta here, and that means that we'll have double theta here in our Mohr circle space, not in the physical space. So remember that angles double when we work with Mohr circle. So that will be our new state. That where our x will go, so to x prime phase and y prime phase. So that's x prime phase, y prime phase, and so that will be the coordinates. And so now we basically just need to calculate these coordinates, which will give us the coordinate here will have half gamma, and the coordinate here will produce us the value of the normal strain here. Okay? And well, we remember that we obtained something small here. We have, right? So that's what we have. And we had 0 on X phase because, well, we don't have any tension here. Okay, so then this is our angle, 60 degrees, so it's 2 theta. And in fact, for us, it would be more convenient to not to work with 2 theta to translate it from what we know from this part of line to this line, but it would be more convenient to work versus the angle here with this triangle. So that will be 2 theta minus that new angle alpha. Because we want to use the trigonometry to calculate things in this triangle. So then that alpha can be calculated based on the coordinate here, which is 50, right? So that's from here or here, more precisely from here. But this angle, this triangle, will be exactly the same as here. And then the distance from here to here is the central coordinate 160. So arctangent of that value will give us the value of alpha, and in the degrees that will be 17.35 degrees. So now I can calculate that other angle, so I just take 2 theta minus alpha, and I will call that beta. So 2 theta minus alpha, so 60 degrees minus what we calculated right here, and so at the end we'll have 42.65 degrees. Very nice. Let's remove all the redundant things and only what we actually need. So we know the angle beta is right here. So we have the radius that we calculated before, a little bit larger than the central point, the distance from here to here. And now we can get to the calculations of the coordinate x here. So first of all, let's start from the normal, from this calculating the normal component of strain. So basically coordinate from here to here. And a way to calculate that would be to take the whole length from 0 to the central point, which is given, right? So that is something that we already know. And then just subtract this part, okay? And this part we can calculate again because we know the radius and we know the angle. So I can calculate this part. And so then I can write that this small tiny part that will be actually our normal component of strain in x prime direction here, that will be the whole thing here, the length here, c, coordinate of the center, minus this smaller part, which is the radius multiplied by cosine beta. So we can do that, right? So substitute things that we already know. And so then we obtain that we have epsilon x prime equal to 36.7 microstrain. And then we can compare to what we calculated with transformation. Should be the same number unless we made the calculation mistake. Alright, so now next step would be to calculate gamma here. Right, so this is basically this coordinate from 0 to here. And that again can be done fully on consideration of this triangle. So we know r and we know beta. One thing to remember here is that we are not getting gamma, but this coordinate is actually half gamma. Right? So that's this half gamma in the new coordinate x prime y prime will be r multiplied by sinus beta. So then that factor 2 I can transpose to the right, and so then our gamma actually is 2r sinus beta. Now I can substitute. R is still 167.6 microstrain, so factor 2 that came from our definition of that circle, and so then the angle that we had for beta, and we obtained a negative value for shearing strain at x. Okay, well, negative would mean that we have this in this direction, similar to here, right? Okay. Then epsilon y prime will be c plus r cosine beta. So that also can be found from considering the exactly identical triangle just right here. So that will be a larger coordinate. So that will be the whole distance from here to here plus exactly this part, which we already calculated here, r cosine beta, but then it was with minus. So the whole coordinate here will be this number. Okay, so it's 160 plus 167.6 and cosine of beta, and then we end up with the positive tensile strain. Sorry, tensile strain for like here, tensile strain for y prime. And that's basically it. Thank you for watching.